Yeah, you can start.
I think basic inequalities today, and mostly AMGM and its application. So I'm assuming people know what AMGM inequality is. If you don't, that's okay. So basically, it says that if I take some n reals, not negative reals, and if I take their arithmetic mean, then it's always greater than the geometric.
By the way, your voice is a bit low.
Oh, okay. What about now?
Yeah,
Was I not audible before? Should I
no,
repeat?
no, you were audible. It was just no, it's fine.
Okay, I'll not repeat them. So basically, the proof I like is using kind of like induction. So obviously, like n equals 1, x1 by 1 is greater equal x1 raised to 1. And then n equals 2, it's basically x1 plus x2 by 2 greater equal root x1, x2. If you multiply 2 both sides, it's x1 plus x2 greater equal 2 root x1, x2, which is just x1 minus x2. So root x1 minus root x2 whole square greater equal 0. This is always true. So that's that. So basically, we can induct this way and kind of prove it for all n as powers of 2. Basically, like summation xi from 1 to 2 raised to k minus 4. This summation xi from 2 raised to k minus 1 plus 1 till 2 raised to k. You can apply AMGM with n equals 2 here, which just gives its product xi from 1 to 2 raised to k, root of half of 1 by 2 raised to k minus 1 is just 1 by 2 raised to k. So that works. But if you want, you can try to prove it for the general n now for a few minutes. Then I'll discuss.
For 3, like you can divide x2 as like I think x2 by 2 and x2 by 2, and then take AMG on 4 terms. But like that doesn't give a strong bond that we need.
Quality case. Because the ideal equality case is that x1 equals x2 equals x3.
Your voice, by the way, it's low.
So the ideal case is when the three variables are all equal. But if you apply AMGM this way, it will be x1 equals x2 by 2, which is x3. And you don't want that.
Okay, then if we divide it like x1 by 3, x1 by, not 3, x1 by 2, x1 by 2, plus x2 by 2, plus x2 by 2. And then in another term, we can take, okay, that also won't work, I guess. Like, okay, that preserves the quality case, but I still don't think that would work here.
Basically, maybe x1 plus x2 plus x1 plus x2 by 2 is p by 2 x1 plus x2. But let's take n equals 3 for now. Wait, I'm sorry. I meant this. We know for AMGM for n equals 4, so let this be x. So x is later equal 4 times 4th root of x, okay, x2, x3 times x1 plus x2 plus x3 by 3.
From here we can get for n equals 3, right?
Yeah.
Okay, I think I see for general also. So basically just add like 2 to the power k plus 1 minus c times the arithmetic mean and take them.
Yeah, so you can prove for n minus 1.
Okay, n equals 2 to the power x minus c. So it's c times the am of the things greater equal. Okay, yeah, so it's raised to n.
Your volume is a bit low.
What about now? There's some trouble with my laptop. I don't know.
Now it's fine.
Cool. Do people see how this is kind of working out with any general n, not just 2 raised to x minus 1 or something?
Yeah.
Okay, so I'll give a problem. So basically, this kind of partitioning was not working because the equality kind of was not holding. So kind of focus on equality cases as well when you're trying to use inequalities, because otherwise it kind of feels very random. Because you can get like at least 100 bounds on x1 plus x2 plus x3 this one. I will give a problem. So basically the problem says that if you have 3 real numbers, positive real numbers with some 3, and if you take root sum of the roots, then it's greater than the sum of product taken 2 at a time.
Like, I think we would have to homogenize, right?
Okay.
I cannot hear you, by the way.
So degree here is half, and then degree here is 2. And by homogenizing, we mean like kind of making the entire expression this of the same degree.
Yeah, so like on the left hand side, maybe we can multiply by like a plus b plus c to the power 3 by 2. And on the right hand side, we'll multiply by 3 to the power 3 by 2 because a plus b plus c is equal to that.
Fractions are really the nicest thing. So you can just try to square it. If you really want to homogenize. Okay. Okay, let's multiply the expression by 2. So that's 2 root a plus 2 root b plus 2 root c greater equal 2ab plus 2bc plus 2ca. We can write this as a plus b plus c raised to 2 minus a square plus b square plus c square, which is 9 minus a square minus b square minus c square. So basically, you want to prove that a square plus 2 root a plus b square plus 2 root b plus c square plus 2 root c is greater or equal to 9.
I see the finish. Can I say?
Yeah, sure.
You can apply AMGM on a square root a root a.
Why not?
Yeah, and this will give this by, this is at least 3a. And you can just add.
So if you add all these 3 expressions, you get this big expression greater or equal 3a plus 3b plus 3c, which is just 9. Do others see
Yeah,
that?
yeah.
Is it okay for everyone? Is it 2020? I'm not sure about the years. So we can have some positive real numbers, and the sum is 2 raised to n minus 1. So we have to find minimum value of this expression.
It's 2021, by the way.
Let's see. 2021. Yeah, it is. Previous recordings you can see on OMC's YouTube channel. Any progress or ideas or anything of that sort?
I feel like 2, 4, 8, 16 dot dot should be the correct solution.
I mean, like
Looks-
1, 2, 4 thing.
Oh yeah, 1, 2, 4.
Maybe some sort of induction on it.
Let's check like a small case and those two.
Also your voice. Thank you.
So let's check a small case. Say n equals 2. You have a1 plus a2 by 1 plus a1. And a2 is like what's 3 minus a1? Can you find the minimum value of this?
Do you want the calculus?
No calculus, just normal stuff.
Also, we could like add 1 to each of the terms and subtract n from it. I think.
Kind of become a1 plus 1 by 1 plus a2 plus a1 plus 1 by a1 plus 1 plus a3 plus a2 plus a1 plus 1. Then a1 plus a1 minus 1 then a1 plus 1 by 1 plus a1 then a1 minus 1. So directly, and you obviously subtract MGM. Directly using AMGM here gives this is greater equal to n times nth root of the product, which is simply just 1 plus a1 plus a2 to an, because this cancels this cancels.
By the way, voice is bit low again.
Oh, okay. Is it okay now?
Yep.
Okay, so the entire thing was this minus n, and this part is greater equal n times nth root of this sum of ai's plus 1, which is equal to n nth root of 2 raised to n minus 1 plus 1, which is 2n. So the original expression is greater equal to n minus n, which is n. So you have a bound now. And so you just kind of need to find the equality case. So you know that this is the minimum value. And this is kind of the equality case. And it's easy to show that it works. Did people follow?
Yeah.
What about others?
Yeah.
Okay, I'll assume it's okay. Will that be okay? Here they're just reals. They don't need to be positive or non-negative, and you have to prove this. This is 2001
Why is the inequality sign flipped?
I'm sorry.
Why is the inequality sign flipped?
I think it's correct.
No, I'm just saying it looks annoying with flip.
That's better.
I guess. Okay, so basically we have to maximize this thing. So we can just assume that x1, x2, xn are all positive, because let's say if some xi is negative, then the denominators are not affected because they are squares anyway, right? So that will stay positive. In the numerator, the ith term will become negative, and the other things will stay as it is. Like they're not dependent on the sign of xi. But if xi is negative, that is basically, huh?
Just might as well switch.
Oh, wait, can you repeat?
Just make it positive because it doesn't affect.
Yeah, that is what I'm saying. So xi's are positive. Yeah, that was what I was saying.
Okay, also try proving this.
Wait, how can we assume xi is positive?
So if it's not positive, let's say some xi is negative, then like if I change the sign of xi, then except the ith term, rest of the terms stay same, and the ith term only increases, and we have to maximize this.
Achha,
We
yeah.
How did this come? Sigma ai squared is less than equal to n times sigma ai squared. Can't hear you, by the way.
I think it's true. Wait, let me check. Yeah, it is true. It's just like a lemma you might use here.
Oh, is this just T2?
This thing,
Yeah, Cauchy Schwarz, right?
try AMGM, please.
No, I'm saying this thing, sigma ai squared.
Oh, that's just, I guess, just expand and do things.
Yeah,
And even that.
yeah,
Yeah, obviously, the Cauchy Schwarz work.
yeah.
This is Cauchy Schwarz, right? Is this like, are you using Cauchy Schwarz or EMGM?
This thing you can do by AMGM completely. You might use this thing, at least in my solution, this sort of a lemma is needed.
Oh, okay.
So the using this thing, the thing we have to prove is basically like sigma xi by 1 plus x1 plus so on till xi squared less than root n. This is not what I got. I got x1 by 1 plus x1 whole squared.
So it's like xi plus upon 1 plus x1 plus
Yeah.
xi squared.
Remove the squares. The squares is like outside of the whole denominator.
Or sum till xi.
Yeah. No. The numerator is xi. The denominator is squared. No. Remove the parenthesis and the square and remove the squares from the denominator.
So it's summation xi squared.
No. Yes. Is less than root n.
Have to put Did you get this?
Oh, right. I'm not sure if the bound is correct. Like the original left-hand side thing is less than the this thing. Like the original inequality, the left-hand side of that. Yeah.
Just directly by this.
Huh?
Directly by this?
The above thing is less than this. Yeah, directly by this lemma. Oh, I might be missing a factor of n. I just realized.
Ever root n.
Also, wouldn't the equality be flipped? Because it's in the denominator.
I feel flip it, right?
No, like I don't see how you got
Like the LHS here is bigger than this.
Oh, it's better.
Because each of the denominators are bigger.
okay. Okay.
Hmm. No, like reciprocate both the sides. So like n by sigma ai whole squared is greater than equals to 1 by sigma ai square. Yeah. So now multiply both the sides by xi on the numerator.
It's xi by x. But then it's like you have 1 to n here, not 1 to I.
You can take it for I terms also, right? Like
Okay.
and just
sure.
better do it I times xi in the numerator. There.
Kind of like 1 plus I times xi.
Why I plus 1?
There's I plus 1 terms in the term. So there's 1 plus 1.
Oh, fine. Yeah, and then denominator of the right hand side. That thing. Yeah, but like this might be too weak, is what I'm thinking.
Yeah, it might be. Plus, it's harder to deal with this now because you have I plus 1 in the numerator.
Yeah, right.
How about you square the initial thing? Now you have x by 1 plus no, x1 plus 1 by x1 plus 2. No, x1 by 1 plus x1 square plus x2 by 1 plus x1 plus x2 plus xn by 1 plus x1 square plus x2 square. You have to prove this basically.
We could apply that lemma on LHS, I think.
Now this, let's say s is less than equal n times x1 square by 1 plus x1 square plus x2 square by 1 plus x1 square plus x2 square and less than not square. We have to prove it's less than n.
So we have to prove x1 square by 1 plus x1 square whole square, and then sum is less than 1.
So like if I decrease the denominators here, then my left hand side just increase and we need to match it. So you can try to decrease some denominators here.
Can you go again? Couldn't hear you.
Okay, so basically, if we decrease the denominators here, your LHS just increases. So, like, if you can slightly decrease you have some sort of freedom to slightly decrease the denominators here. Since it's strictly less than n.
We can maybe remove the squares. Like instead of 1 plus x1 square plus x2 square, the whole squared, we can remove the whole squared.
Or we could write 1 plus x, but I think this is false because x1 all 1 just gives us harmonic, and that can get as many as big as we want.
Why are we multiplying by this?
So basically, I reserve one factor and then I reduce the xi squared term in the ith fraction and the other thing. Like this thing is still greater than this thing. Right?
Yeah.
I reserve one of them and then change the other one.
Right.
Can we telescope now?
So this thing minus this thing is the numerator. This thing minus this thing is the numerator. So it's
Yeah.
1 minus 1 by 1 plus x1 square plus 1 by 1 plus x1 square minus 1 by x1 square plus x1 square. And that's like 1 by 1 plus x1 square and xn minus 1 square minus 1 by 1 plus x1 square plus x2 square and xn square. So we need to prove that this thing is less than n. Wait, less than 1. Sorry. This is obviously true. Does that make sense?
Yeah.
Yeah.
Should I go over the entire proof point?
Your voice is a bit low.
I'll go over the entire proof once because it was slightly lengthy. So basically, first, we kind of squared the entire thing. So we get a nice factor here. And using this lemma, we can also cancel the ends. So we squared the entire thing and then we got this square thing. The initial thing should be less than equal this new thing because of the lemma which we can prove using Cauchy Schwarz or expansion or AMGM. Basically, any kind of inequality works here. And we have this thing. So we kind of need to prove that this thing is less than 1. This was the original thing, sorry. So using the inequality, the lemma thing, we get this thing should be less than equal, strictly less than n. So we cancel the n's and we have to prove the thing in the bracket is less than 1. And then we know that if we increase the denominator of something, the actual the number decreases. And if we decrease the denominator, then the number increases. As long as the other things stay constant, like numerator. Yeah, so we decrease the denominator of each of the terms by a factor kind of xi square. We remove 1 xi square in the denominator, and then we form a telescopic thing, and we get that it's less than 1. Is that okay?
Yeah.
slightly different problem.
Uh, I have a way to homogenize it, but I don't know how to proceed further. Like you know that sigma a whole squared is equals to sigma a squared plus 2. So you replace 2 by sigma a whole squared minus sigma a squared. That will give you 6a square plus 3b square plus 2c square greater than equal to sigma a squared, a whole square. Yeah. Also, you're not audible.
That does work. B square plus B square plus C square. Yeah, that is true. I'm not sure if that directly helps.
That reduces it to proving to 4a square plus b square greater than 1, right?
Yeah, but that's not really true.
Yeah. Oh, is it not?
Because like if you increase A and B, like
Yeah.
you can still find some field. Like try to use some inequality or something. You have some term here and some term here. You would like to have something of this sort. So that when you add, you have like K here. And you have this thing. 5a squared plus 2b squared plus c squared here. So kind of try to do that.
Okay, I see how to do it, but like I'm kind of lazy to compute the expression, so can I just tell you the method? Cannot hear you, by the way.
Sure, go on.
Yeah, let's say you have xa square plus yb square, that will be greater than equal to 2 root xyab. And then 5 minus, so now like you, when you add the stuff, the method you said, you would want that the coefficients of a add up to 5. So 5 minus xa square plus zc square must be greater than equals to 2 root, like, yeah. Right. And similarly for the third term, we are left with like 2 minus y and 1 minus z. Isn't it a lot tilted now? Okay. And now basically these three things should be equal, and these three things together should add up to 1. So that will give you that each of these things should be individually 1/9. The thing inside the square root. So like xy must be 1/9. 5 minus x times z. Yeah. This should be equal to 5 minus x times z.
Yeah, like all these three equal and they are all 1/9.
Yeah. And now you can just like use the xy thing to write y in terms of x and use write z in terms of x. And then use the third expression to get value of x. And then you can compute x, y, z, and you can put in the coefficients and you'll be done.
Yeah, yeah.
There is a possibility that this doesn't work. Like one of the x, y, or z's are coming out to be negative or something. Can you check it out?
Yeah.
So basically what I'm trying to say, if it does not work in some case, you can just like change these things a little bit. You can add a thing such that a squared plus b squared plus c squared times, let's say alpha greater than equal ab plus just alpha. It usually does work, but I think in this case it's not working. You can just add this factor and it will work. I really don't want to compute right now, so I think we can move on to the next problem.
How does adding this factor help us?
Like just in case the things you did.
Yeah,
then,
I understand when you have to, but like, how does this help you?
like if it's negative, then you can kind of like add this thing, and then the constants change slightly. If that makes sense. You can kind of get a positive thing.
Can you give an example? Like, just take alpha as like,
Okay, like I don't really want to compute anything. So basically, like to get something like a squared plus b squared plus c squared, you actually get like one this, one this, one this, right?
yes.
And then you like half of each of these.
Yeah.
But if you directly write it, you don't need like each of these things. So you kind of have like a lesser thing, if that makes sense.
So you're not taking the first three expressions, you're directly taking the alpha a squared plus b squared plus c squared.
You're taking all four of these.
Okay, so like the first is x a squared plus y b squared. Then the second thing will be 5 minus x minus alpha times a squared, right?
Yeah.
Okay, and so in the last expression, after doing the AMGM, you'll get this should be greater than or equals. Oh, you take two terms at a time, so that you get. Okay, yeah, I see.
Is that okay for everyone?
Yeah.
Can you give a hint?
Kind of try to find the equality case.
The equality case is 1.5, 0.5.
Like 1.5, 1 and 0.5. It x equals them, y equals them.
Yeah.
Okay, so your ideal value of this expression would be 16. This expression would be 8. And this expression would be 16. Yeah. So simple stuff, you would like to have something like 2x plus 13 plus.
By the way, I'm not able to hear you clearly.
So since the power is like half, so you would like to have something like, so 2x plus 13 plus some constant greater equal root 2x plus 13 into c. And you want c to be like 16 because equality case. So you kind of get like 2x plus 29 greater equal 4 root 2x plus 13. Did that make sense? Like why you would want something like this?
Yeah.
How did you get C as 16 though?
Because in the equality case we have is when x is 1.5.
Huh?
So the 2x plus.
Oh, yeah, I see.
So from here you have 2x plus 13 raised to half less than equal x by 2 plus. Wait, this is 2 times this. X by 4 plus 29 by 8. Now similarly try for each of these things.
For the y thing, you get that cube root of 3y plus 5 is less than equal to y by 4 plus 7 by 4. Like you just take 3y plus 5 plus 8 plus 8 and AMG on that. Yeah. So now we can sum up, right? And then x plus y plus z is 3. Yeah, this comes out to 64 by 8, which is exactly it.
Is this okay for everyone?
Yeah.
Yeah.
I have one more problem, which is slightly easier, but who cares? This is actually Chinese girl math Olympiad stuff. Okay, I should write the source. CGMA 21P1.
Okay, so if we like let's say we take the first two terms and then we combine the denominators. So we'll get that the first two things add up to 1 plus a1 plus a2 divided by 1 plus a1 into 1 plus a2. Now if we involve the third term also, plus a1 a2 divided by 1 plus a1 plus that thing. So that will essentially become a1 a2 a3, yeah, plus a1 a3. So which is basically just like 1 plus the sigma ai plus sigma ai aj, so on. So combining till all the n terms, you'll have like all the terms taken none at a time, one at a time, two at a time, and so on, till n minus 1 at a time.
Is it like 1 plus A1 into 1 plus A2? So 1 plus AI minus product AI.
Yeah. So now this thing is basically like 1 minus product AI divided by product 1 plus AI, right?
It's obviously less than
Wait, can you say it bit louder?
which is obviously less than 1.
Yeah.
Or what you could do is you could work backwards, since an only affects the last term, and the more you decrease an, the larger this value becomes. You can just put an as 0. And then you get something like product AI, not including an, product 1 plus AI. And if you add all these terms, it's like the product is sum is exactly 1. So this thing is called smoothing. You just take like some isolated term and you see how it affects the general expression and make changes accordingly.
How did you take an as 0?
Oh, you're not audible, by the way.
Since an only affects the last term, we can kind of, and we don't have any condition on AIs. So the more we increase AN, the smaller this value is, and the more we decrease AN, the larger this value is. So the maximum value of this is when AN is 0.
Ah, yeah. Okay, right. So like we can take the equality case for that, I think. You're not audible.
Do you guys have any questions? I'll not do any more problems now. Hello.
Yeah, no questions.
Yeah. Should I stop recording then?
Yeah.
Okay.